a little bit of motivation. Part of the reason we're doing this is, if you look in the test lab software, you'll often see menus like this where it says things like, hey, Spectrum, Autopower, PSD, Power. So it might be, kind of confusing. Which one should we pick and why is one the default and not the other, et cetera. And I guess another thing to kind of point out about this, you might be even using different data acquisition systems, and the names could be slightly different. So this word Spectrum, in test lab, it means a certain thing inside the Siemens software, but in other pieces of software, they might call it something else, but the concept will be the same. So there's certain things to look for when you select one of these items. For Spectrum, in our case, is a thing with amplitude and phase, and Autopower has no phase. And I'll kind of try and show that as I go along here. So a spectrum means that we're going to take some time history, and this time history, we're going to decompose it using a Fourier transform into a set of sinusoids. And we can then look at these sinusoids, they have a certain amplitude and they have a certain frequency associated with them. So you can see the frequency domain representation of this data, where you can see the amplitude and frequencies of the individual sinusoids that make up this time signal. For a given time domain signal, and this is kind of key to the whole Fourier transform, there's only one set of sine waves that sum up to give you that signal. So it's a unique set of sine waves, right? In other words, there's like a one-to-one correspondence between the frequency and the time domain when you use the Fourier transform to go between. And it's helpful to look in the frequency domain for a given time signal because we can see the constituent components. And I always kind of joke, it's very useful. We know who to blame for a given noise or vibration problem. We can see like, 60 hertz is really big. I know that's the compressor. They're to blame for the problem. The fan, which is running at 180 hertz, that's very low amplitude. I know it's not to blame. So I pick on the compressor person and not on the fan person, for example. Let's actually try it, see what happens. So I got the software here, and let's start with nice, like a sine wave. So I got the sine waves here, okay? And I put the same sine wave in the top and the bottom. If I was to kind of zoom in a little bit, I think you can see it looks like a nice sine wave, right? Let's say I take this sine wave here, click on the button here for Fourier transform, and it just does a Fourier transform, no parameters, no window or anything like that. I now get a FFT, and I can say, okay, this sine wave must have been right around 100 hertz or so, right? Yeah. And then if I click on this again, I'm going to hit the Fourier transform button, and it'll do the inverse Fourier transform. Will that look like this original sine wave? All right, let's see. Huh? I think it's looking like it. I was going to maybe zoom in a little bit here on both. Yeah, looks pretty good, pretty identical. So we can take data from the time domain to the frequency domain and back through the Fourier transform, get the same result. But a sine wave is pretty simple. Should we do something maybe a little more complex? Yeah, I got a folder here called complex. I think it has a complex signal in it. Got that at the top. At the bottom here, I'll hit FFT. Oh, now this guy's got like some noise all across the band, and it looks like there's 100, 104 or so frequencies in it. So, all right, I'm going to hit the FFT button and go back again. And what do you think? Does it look like the original?
It does.
That's exactly the point that we wanted to make. We're hopefully demonstrating that there's this ability to go back and forth. And one of the key things that you can kind of forget about sometimes if you're not careful. If I go back here we showed the spectrum, right, of these sine waves, but I only showed the amplitudes. But to really go back to the original signal, besides the amplitudes and the frequencies that these things occur at, what else do I need, Charles?
The phase.
Yeah, I need the phase. And that means, like in this example, I got two sine waves, a red one and a blue one. They're the same amplitude, but when I do the Fourier transform, and I guess the spectrum is just the raw or straight up Fourier transform, you can see amplitudes come out the same, but the phase is different. And that's how it knows how to reconstruct that properly back in the time domain. It's got to have that phase information to do so. When I was showing this here, I was, like if I had that sine wave, I was only showing the amplitudes when I did the Fourier transform. But if I grab this sine wave and I do the FFT, there's a amplitude and a phase. And I used a plot here called a Bode plot to show both at the same time. So that was key to being able to go back and forth, even though we didn't see the phase in this regular front-back display. It was still using it behind the scenes, if you will, to show that. Well, key takeaways: any time domain signal can be described with a unique set of sinusoids, and these sinusoids have a specific amplitude, frequency, and phase, and no information is lost. We can move back and forth. So now let's go to the next topic, this autopower. And to introduce the topic of why an autopower exists, we'll do a little mental exercise. Here I have the sine wave, right? And you can see it goes from 0 up to 5, down to -5 over time. And sometimes, to eliminate noise and other things, we do some averaging. And so let's say this was my first little acquisition, and then I did a second acquisition on the same sine wave. Is this sine wave any different in amplitude, Charles?
Not in amplitude.
Not in amplitude, but what is different about it?
The phase is different.
Yeah, so if I took these two and I averaged them, then I would get a 0.
Yep.
That's interesting. So yeah, if you're trying to reduce the vibration, that might be a good thing, right, Charles? You could just
on paper, it gets you out of the room until they drive the car.
Yeah, the thing is vibrating at 5 Gs or whatever, but I'm reading 0. So averaging spectrums can be a little bit problematic, and that is why we do autopowers. And autopowers do a little trick on the signal to eliminate this problem of averaging to 0. Okay, the trick is they square the signal. Do you see how this is squared here, Charles?
Yep.
So this thing that was 5, if it's squared, it becomes 25, right?
Yep.
And then here we had -5, but -5 times -5?
25.
Yep, 25. So we've made these the same. And then if, we had the inversion going on, -5 and 5 here, well, both of these squared to the same thing, 25. So is our average 0?
Nope.
Nope. So good. Well, and then we do the Fourier transform of this, and it's great. And so we square it before we average it. Let me switch to the software again, and let's play around a little bit with the autopower. I got a 5G sine wave here. So we first of all said if, let's say I grab this sine wave, 5Gs here, and then I do the Fourier transform, it has phase, right?
Yep.
So we had established that before. But let's say instead I take the sine wave, and instead of doing a straight up Fourier transform, this third button in here says averaged autopower spectrum. And here I have a few more choices. And I can say I want 2048. Uniform is no window. Overlap is 0. I hit OK. Hey, look, I still got a sine wave, Charles. Do you see that?
You do.
Yeah. Right around 100 hertz there. But there's a few things about this sine wave. The first thing is it 5 G's amplitude here?
No, it's squared. 25.
Yeah, it's squared. It's 25 G's in amplitude, which is kind of funky. But by squaring it, what did I successfully do?
It looks like the phase is 0 now. It's eliminated.
It is 0 across the board because it's an all real function by squaring it. So I eliminated the phase problem, but now I'm left with 25 G's squared. Is that good?
Depends on how you like to look at your amplitudes. But,
Yeah. So a lot of people, when these Autopowers came out at first, it was actually they'd leave it like this, and so you'd end up with units like 25 G's squared. But to get back to 5 G's, is that possible?
yeah, it's possible.
Yeah. All I have to do is take the
Square root of
square
it.
root of that, right?
Yeah.
And then instead of 25 G's squared, I'm back to 5 G's. Let's look back there. So we actually have a nice little button in the software here. So I'm looking at 25 G's squared. And well, let me start by saying I could have, let's say I took that sine wave and I did my Autopower. I can pick here peak power, but I could also say peak linear. See that?
Mm,
And if I hit OK,
that should be
then it
5
does
with no
a
phase.
square root operation. So that actually kind of makes a little bit more sense. Would you agree with that?
Yeah, be less questions.
Yeah, a lot less questions when you're in that meeting. Oh,
Yeah.
the vibration's 25 G squared. So back in this menu where we had the two types of autopowers, notice there's one called linear autopower and power autopower. Which one do you think is 25 G squared and which one is 5 Gs?
I'm gonna go with 5Gs being Autopower's linear and Autopower power being 25G squared.
I think you're absolutely right. So, well, and that's an important distinction. And it's kind of, again, a bit confusing. Here we have the word power because we're going to square it. But if we take the square root after, that's how we get back to quote unquote linear units. So we square it and then take the square root. That's why you have the term Autopower linear. If we just left it squared, then it's Autopower power. An interesting thing, if you're doing something in the software like this, and you're doing a calculation here like the RMS value. What is the RMS value of a sine wave, 5G sine wave?
The peak times or divided by the square root of 2. The
Yeah,
times. Yeah.
or times 0.707 or something like that.
Right.
So yeah, if you have a sine wave, right, the peak value here is 5. You can also get a RMS value that's 0.707 of the peak, right? And
Yep.
so really when we do this FFT, sometimes they'll express the sinusoids in RMS amplitude values, which is, it's not the peak and it's not the trough, or they'll express it in peak values. So that's actually a selection in the software. And this again gets maybe a bit confusing. There's also peak to peak. So we had linear peak, right? This was like 5 Gs. This one squared was 25 Gs.
Squared.
But a linear RMS would be this 5 Gs times 0.707. And we can pick RMS. We can also pick peak to peak, which is twice the amplitude. And we can have that in both power and in linear units. That's not confusing at all, right, Charles?
We just give you a lot of options.
Yeah, so let's look at these options in the software again. First thing I wanted to point out, so to do RMS, you add a double X cursor and you just right click, calculate RMS for people that were interested in. And so that's 3.54 is 0.707 of 5 Gs. But it's also possible when you do like the averaged Autopower, you can actually choose whether you want to see things peak to peak or RMS or what have you, and whether you want to leave it in linear or power. That's why you have some of these choices. Or if I'm just looking at a spectrum, the second button in is this FFT format conversion. Right now, this is a peak linear, but if I wanted to see this in RMS linear, and I hit OK, and maybe I have to add another digit here. I should have had. Okay, so it's optimized. 3.54 matches 3.54, right?
Yep.
So I can switch and show it in RMS if I want. And by the way, over here under options, you can also say things like you want to see things like the spectrum scaling and the spectrum format, so if that's an RMS or a peak value. Would it matter if you went in a meeting, Charles, and you're like, hey, that thing is 5Gs, and you were talking peak, but everyone else thought you meant peak to peak?
Yeah.
Yeah, it could really kind of screw things up. So it's important to know which is which, right? So yeah, we can do RMS or linear. Another format here. So if I said peak value and power, it was on this 5G sine wave, what do I expect this amplitude now to be?
25 the square of it,
It
G
should
squared.
be 25 G squared. How
Yep.
about this RMS value? Will that change?
No.
No, the cursor is actually smart enough to say he changed it. He's looking at 25 G squared power peak, right? Peak power, but the RMS is still the same because it knows the square root and it knows to take 0.707. And so, yeah, in a way, it doesn't matter what I pick here. If I had RMS power, it changes again, but the RMS here remains the same, right? Because RMS power is squared, but
Yep.
anytime I pick this thing RMS, I get the right value. So hopefully that made a little bit of sense, and we got rid of the phase. Which one do you like best of all these choices, Charles?
Uh, I don't know, maybe for vibration, like linear peak, and maybe for acoustic stuff, linear RMS. What do you like?
Yeah. Yeah, an overall level, like you hear in acoustics, like that car was 60 dB overall, is usually by definition RMS. But a lot of times the people like peak values, for vibration, because you want to know the peak, or peak to peak. So yeah, it kind of depends. But in either case, you didn't really like power, I guess, Charles.
I didn't.
Thinking about so a lot of choices there, but yeah, at any company you got to decide which way you want to display it and report the values, and do that consistently for comparisons' sake.